That's recorded.
So hi everyone, this is our first DEF CON and we're very excited to be here. Today we're going to share our analysis. Oh, thank you very much, thank you. We're going to share our analysis and exploitation of a CVE that was found by the NSA about CryptoAPI. Something happened, okay. My name is Tomer, I'm a security and vulnerability researcher at Akamai Security Group. I'm a gamer, I practice Krav Maga, and you can find my research on the GitHub link on the slides right now.
Hi, I'm Yoni. I'm a Windows internals and OS fan, and I enjoy math and, of course, cryptography.
Awesome. So, for those of you who don't know, each month Microsoft releases an advisory online named Patch Tuesday. In this advisory, they release around 100 or so security fixes for everything they found and patched on that month. And on October of 2022, we found something that was very interesting to us, the CV that you can see on the screen right now. It was interesting to us for several reasons. One, it was a critical vulnerability, and only around a tenth of the vulnerabilities are critical. Two, it was disclosed by the NSA, and their vulnerabilities tend to be very impactful. Three, the vulnerability was highly likely to be exploited online, which meant that there might have been somebody who, in the wild, who used it. And four, nobody was talking about it. According to the advisory, an attacker would be able to spoof their identity over anybody they want online, and that was definitely something that was worth digging a little bit deeper into. We did that, and we want to share our analysis of that today with you. But before we can do that, we wanted to give you a little bit of background. So, what is CryptoAPI? CryptoAPI is Microsoft's main way of handling everything related to certificates. It is responsible for encryption and decryption, but for us today, it is mainly responsible for the validation of certificates. It is mainly implemented in the Crypt32 DLL, which is going to come into play later on. Now, just as a quick reminder, when a website is serving us a certificate, it will serve us actually a chain of certificates. And going from the bottom upwards, we can see the end certificate, which the website owner is going to use to sign stuff. We then have the intermediate CA, which is going to sign the end certificate. And we have the root CA, which is going to sign the intermediate CA, and is going to be pre-trusted on all endpoints, such as Linux or Windows. It can be DigiCert or anything you know from your daily lives. Now, you might ask yourself, why are certificate validations so important? Well, certificates today are our main way of ensuring trust between one or several parties. And for example, when we go online, we want to make sure that the site that we are reaching is a legitimate site and not just a malicious one that can cause us harm and do stuff that can cause us harm, sorry. Yeah. So who uses CryptoAPI? CryptoAPI, as I said, is used by Windows extensively for code signing and driver signing. It is used by some web browsers such as Chrome and Edge. It is used by data transfer clients such as Cal and wget. It is used by FTP managers, and it is also used by EDRs. And there are many other applications who use it. Now that we have a little bit of background, we wanted to talk about how to locate this vulnerability. We used ITA to reverse engineer the vulnerability, and we used BinDiff to compare between the patched and unpatched versions. What you can see on your screen right now is the output of BinDiff for Crypt32 DLL, and the image that you see is actually a list of functions that have been changed and their similarity rating. A similarity rating of 1 means that nothing was changed in the function, and below 1 means that something has been changed. As you can see, only one function has been changed, and what could that mean? Well, if a lot of functions have been changed, that might mean that the file has gone through reformatting or refactoring. But if only one function has been changed, that might mean that there was a pinpointed effort to eliminate one singular problem. That was interesting to us, and we wanted to see what was actually changed. Now, when we took a look at that, we could see that this is how the function looked before the patch, and this is how it looked after the patch. 2 mem compares were added, and that obviously meant that something needed to be validated even further. And And near the compares, we could see some references to a caching mechanism, which is going to be very important for this vulnerability, and we're going to touch on it later on. Now let's talk a little bit about who is getting compared. Now, when we analyzed the entire function, we could actually see that this was a lookup function, and what was changed was the way the certificates were validated. Before the patch, if a certificate was found in the cache, it would just have been returned and the function would have continued. And after the patch, the two compares would actually compare between the data of the input certificate and the cache certificate, and only on success would it have been returned and the function would continue. Now that we know where the function is, let's talk about reaching the vulnerable code. Reaching the vulnerable code, we wanted to reach the root win API, and doing so was pretty easy. We cross-referenced twice from the internal function and got to cert get certificate chain, which is the root win API. Now we wanted to get to win API because win APIs are a set of functions that allow any user to invoke them from their code. Yeah. So this is how the function looks in MSDN, and I want to take a few minutes to talk about the parameters of cert get certificate chain. We have cert context, which is going to be the input certificate. We have flags, which is going to allow us to enable the caching mechanism. And we have chain context, which is going to be the output parameter, and this is where the validation is going to take place against. This is the specific flag that needs to be set in order for the caching mechanism to be enabled. This is called cert chain cache and certificate. As I said, it's going to enable the cache. Let's talk a little about the end certificate cache. And when we analyzed it, we actually saw that this was actually a hash map containing the certificate objects, and they used the MD5 as the indexer for everything. This is a reversed engineered line, and this is how an entry would actually be retrieved. You can see that a cert is getting MD5 hashed and then being offsetted from the hash map start and retrieved into the entry, to the function. Sorry. Okay, so let's see an example of how that would look. Let's say that we have an application who uses these certificates. The certificate validation from Crypto.API. And the application will go to akamai.com. Akamai.com will serve a certificate, and it will be verified, like we said, from the intermediate CA, the root CA, and the end certificate. And after it will be verified, it would go into the certificate cache alongside its trust status, not only the certificate. So the next time that Crypto.API sees a certificate that has the same MD5, it will actually trust both certificates, the certificate from the cache and the certificate that was given, because it will take the trust status from the certificate in the cache. So, as I said, the next time Akamai will try to go to Akamai, and Akamai serves the certificate. The certificate and the trust status will come from the cache and not from the given certificate. Now, let's do a little bit of a recap on the validation process, just so everybody understands it. The certificate validation process takes an input certificate as its parameter. It does an MD5 on it and try to set it in the cache. In the unpatched version, if the certificate is found, it will just have been returned. And on the patched version, the compares will compare between the actual data of the input certificate and the cache certificate, and only on success, it will return. Based on what we now know, let's hypothesize about how an attack would actually look like. So let's say that we can serve a legitimate looking certificate to the victim. The victim will then take the certificate and place it in the cache alongside its trust status. And the next time that we serve a certificate, maybe a malicious looking certificate, the victim will take the trust status from the certificate in the cache and not the certificate that was given. Therefore, we can spoof our identity over anybody that we want online. Yoni?
Yes. Okay, before I continue, I just want to emphasize that the use of MD5 so far does not maybe seem like it has to be suspicious, because it's just a hash table, right? Hash tables have weak hashes, not cryptographically secure hashes, as a thing that usually happens. But usually when you have a hash table, you would then do a comparison And this is what the patch added. Before the patch, there was no comparison, just based on the value of the MD5. So let's see what we're going to be able to do with that. So as Tomer described, there is a theoretical attack possible, which is what Tomer described in high level. I'm going to dive a little bit deeper into it and illustrate what the phases of the attack would be. So the first phase is going to be a cache poisoning phase. So you serve a victim with some valid, trusted certificate so that it would be put in the cache, in the end certificate cache of the victim. So then now it's there, and since it's valid and trusted, the cache is going to say, okay, this is trusted. The second phase is going to force the victim to look up the cache, but with a malicious certificate that has the same MD5 value as the previous valid one. And then the malicious certificate is not going to be validated. Instead, we'll just take the trust status that was previously computed on the valid certificate, and then we'll enjoy the use of the malicious certificate. This is basically phase 3. We just have the malicious certificate be in use, and then we can do our malicious things. But what are the malicious things that we're going to be able to do? Like what are we going to put in our malicious certificate? So let's just remember what's in a certificate in general. There's many fields and extensions that go into X509 certificates. The 3 most important ones for now are the subject, where, for example, for SSL, the subject is where you would put the domain name of the website that this certificate is for. There is the public key, which matches the private key of the website. And then there's a signature, which is signed by the CA that issued this certificate, for example, DigiCert. So what prevents us as an attacker from using this, the official certificate from a website, let's say Microsoft.com, what prevents us from using it to spoof the website and serve it ourselves? The thing that prevents us from doing that is that we don't know the private key. We have to know the private key in order to serve a website with a certificate. So what would be our wish for a malicious certificate? We would just change the public key. If we were able to change the public key to a public key that we know the private key of, then that could be used to spoof the website and serve it ourselves. So that's our goal is going to be to create a certificate that has a different public key. The question is now, can we actually build such a malicious certificate? Can we replace the public key in a way that the malicious certificate and the official website certificate would have the same MD5 value? This is where we get into the crypto. So it would be the best and like the dream would be to have something like a second pre-image attack. So I'll describe that. In a second pre-image attack, we would take this any input string, for example, the valid certificate from the website, and we would modify it, like change the public key, and we would modify it in such a way that algorithmically or mathematically we would figure out a way for it to have the same MD5 value as the original certificate. So this would be the dream, right? If we could do this, we would just take this malicious certificate and just serve it using the attack that was previously described. Unfortunately, nobody knows how to compute a second pre-image for MD5. The only thing that we do know how to compute is MD5 collisions. So that is a bit weaker than a second pre-image, but let's see if this helps us in any way. So let's talk a bit about MD5 collisions. MD5 collisions came to be known 15 years ago in 2008 when this group of researchers that are listed in the middle of the slide published research at the end of the Chaos Computing Conference in 2008, where they showed an MD5 collision-based attack that would allow them to spoof website certificates. So this is very similar to what we're trying to do here, right? The only difference is that back then in 2008, they attacked a certain SSL CA, which signs the certificates using MD5, right? So since 2008, since these guys, that never happens anywhere. Nobody uses MD5 for certificate signatures anymore. And yet, in this context that we are talking about now in Windows, MD5 is being used, but in a different way. It's being used as an index to a hash table. Okay, so we can't directly apply their research, but we can maybe get inspired by it. So they, in their research, they computed MD5 collisions. So let's talk about MD5 collisions. The simplest possible MD5 collision is what we call a simple collision, or an identical prefix collision. And in this type of collision, you have two strings having the same MD5 value. You can maybe have like a prefix, and you append then two different strings, and then you get the same MD5 value. And in 2023, this can be done in a few seconds on a laptop. This is a very non-complex, in terms of complexity, computation. So I'll just illustrate this graphically. So we choose some prefix. It can be anything we want, and then we append two computed collision blocks to it, A and B. And A and B are going to be different. Obviously, if they were the same, it wouldn't be interesting. So they're going to be different. And as a result, we would have the same MD5 state after appending A and B. And when I say same MD5 state, I mean they have the same MD5 value, but also the internal state of MD5 is the same, so that we can also continue adding a suffix, and it would continue to have the same MD5 value. So as I said, this can be done in a few seconds on the laptop. So you have this pre-made Docker image that, so it's 2023, we have Docker. In 2008, they didn't have this. But these days, it's just like a one-line Docker run command. So I'm going to demonstrate this right now. So if you've never seen MD5 collisions before, this is kind of exciting. It's always exciting to see two different strings with the same MD5 value. So we're going to have like a prefix. I'll start our story here. And then I'm going to run this package called fastcoll. This is just the Docker run line that you saw in the slides. And this should take really a small amount of time, like 1.04 seconds. And then you have two strings, message 1 and message 2. Let me just hex dump them real quick. Oh, well, just lower the font size a bit. There we go. So that's message 1 and then message 2. So you can see that they have, you have our prefix, and then we have some blocks added to it. If you look really closely, you might notice some differences between the two strings. But to make it easier for you, I'm going to XOR them. So this is just a like small Python script that XORs two files. And then you can see here that the XOR has a few bits that are turned on. So the 80s are 1 bit, the 1 is 1 bit, and the 7 is 3 bits. So there's a few bits that are different between the two messages. And yet, if we compute their MD5 value, you can see that they have the same MD5 value. And then we can continue to, like I showed in the slides, we can continue to add a suffix to them. Okay, so we'll do something like, okay, so I appended some string to both messages. Oh, not this one. Like, yeah, I append this to message 2 and message 1. And then you can see that they still continue to have the same MD5 value. So this is really cool. Let's talk about the second type of collision that's possible with MD5. So the second type of collision is going to be a chosen-prefix collision. This is more complicated to do. And the difference between this and the same prefix collision is one small difference, but this is a big difference in terms of computation. The prefix does not have to be the same anymore. We can choose two different prefixes to start with. And this no longer takes a few seconds. It takes a few hours, and you need a GPU to accelerate some of the computation. But so I'm not going to show it live right now, obviously. But I'll just illustrate this graphically, like before. We take two prefixes, and there is no restriction on the prefixes except they have to be the same length. But besides the same length, they can be any strings you want to use. And then you append two computed collision blocks, A and B. And after this append, you have the same MD5 state. And you can continue to have the same MD5 state by appending an identical suffix. So as I said, this is much more difficult to compute. However, a few hours is still not difficult. You can do it today if you want. Okay. Now the big question is, can we use MD5 collisions as opposed to a secondary image to construct a malicious certificate? Can we use this? And the difference is the reason why it's more complicated is that, remember, in MD5 collisions you have to modify both of the strings, not just one of them. You have to append the collision block to both sides. So it seems like it might be difficult or impossible because you have this valid certificate that maybe you can change. However, we did find some trick that enables us to do this. So yes, the answer is we can do this. To explain how this is going to be done, we have to dig a bit deeper into the structure of a certificate, how it's actually constructed. So as per RFC 5280, a certificate is a structure containing 3 fields, and this language here is a language called ASN1, Abstract Syntax Notation. It's a language that describes structure in a way that is canonically serializable as a binary. A certificate is a sequence containing 3 fields. The first field is called the TBS certificate, and the TBS certificate is everything interesting about the certificate. So TBS stands for to be signed. This is the part of the certificate that is being signed by the CA. So the TBS is going to contain the subject, that is the thing that contains the domain, and also contains the public key and all the other certificate fields that they didn't go into. And then the second and third fields are the signature, algorithm, and value. So the signature value is the actual signature. This is signed by the CA, and it's going to sign the TBS. And the signature algorithm describes what algorithm is being used to compute the signature value. So for example, the signature algorithm might be RSA with SHA-256, or it could be like ECDSA with some elliptic curve, and it could be like many other possibilities. And then to go back to the MD5 that we talked about earlier, the MD5 that is used in the end certificate cache that Tomer described is going to be the MD5 of the entire certificate structure. So the TBS and the signature. The entire thing is getting MD5'd, and that is the key to the end certificate hash table. That is called an MD5 thumbprint as opposed to an MD5 signature. So the certificate is like, it could be SHA-256, RSA 2048, it could be like something strong, but MD5 is on the entire thing, not as a signature. Okay, so it seems like we have a puzzle here where we have to modify a certificate without modifying it, because we take like the valid trusted certificate, like the website certificate from, let's say, Microsoft.com or whatever website we want to spoof, and the reason I'm saying that we have to modify it without modifying it is that it doesn't seem like we can touch anything here. The TBS we cannot touch because it is signed. We cannot spoof the signature because it's signed by the CA, by, let's say, DigiCert. We don't have their private key, of course, and we cannot re-sign. We cannot touch the TBS. The signature also has to continue being correct because, remember, in the first phase of the attack, we're going to poison the cache with a trusted certificate. We cannot break the trust. The only way for it to continue being trusted is for the signature to continue being correct. It doesn't seem like there is any room here for playing games. We cannot touch the TBS, and the signature has to continue being correct. There is nothing else in the certificate, that's all. So what do we do? The key to doing something here is to notice that the signature algorithm field, the second field in the certificate, it's not a basic ASN1 type. It's a type called algorithm identifier, which by itself is also defined in the RFC. So if we go further down in RFC 5280, we have the algorithm identifier also defined as a sequence containing 2 fields. The first field is the algorithm. This is a basic ASN1 type object identifier. This is going to be like the identifier of RSA with SHA-256 or whatever algorithm is used. And then there's a parameters field. The parameters field is marked in the RFC as optional, and the meaning of parameters depends on what the algorithm is. So for example, in let's say if you use elliptic curves to sign, the parameters might say what elliptic curve is being used, for instance. If you go to RFC 3279, it's a different and related RFC. You can see what happens in the case of RSA certificates. If you have an RSA certificate, which is very common, right? RSA certificates are like, I would say half of the certificates at least. Then the parameters field has to be there. It can't be omitted. So the standard says it's optional, but in the case of RSA, it has to be present, and it has to have type null, which means it has to be there. It has to be there, and it has to have no value. In the case of DSA or ECDSA, it has to be omitted, but in the case of RSA, it has to be there and it has to have no value. It turns out that if you look at implementations like CryptoAPI and OpenSSL, they don't care what the parameters are in the case of RSA. So it has to be there, that part is still checked, but they don't care if it's null or if it's something else. So it could be, let's say, a bit string, and a bit string can contain anything we want. And remember, the algorithm identifier is a field that describes the signature, so it has to be outside the TBS. This is not signed. So this is something that we're free to change, even in the signed certificate. So let me just recap the structures. So we have the certificate, which is a TBS algorithm identifier and signature value. And the algorithm identifier has an object identifier and also parameters which we're going to change to a bit string, which is going to be ignored by CryptoAPI, and it's going to contain whatever we want. And that's where we're going to hide our collision blocks, our MD5 collision blocks. So let's see how this is done. We take two certificates, our valid certificate, which we grabbed from the website that we want to spoof, and our malicious certificate, which we obtained by changing the public key to a public key that matches a private key that we own. Now let's look at this from the point of view of someone who is computing MD5 chosen-prefix collisions. So the TBS is going to be our MD5 prefix. This is the same length on both sides, and it's a different string, but we don't care. And then we're going to use this RSA parameters field trick to add some more data, where we're going to compute MD5 collisions and just put our collision blocks there in the parameters field. At this point, at the bottom of the parameters field, we're going to have the same MD5 internal state. But this is not a complete certificate yet, because a certificate also has a signature value. We only have a signature algorithm. So we're going to continue by appending the signature value of the original certificate on both sides. On the legitimate side, this is going to be a correctly signed certificate because the TBS is not changed, the signature value is not changed, and the signature algorithm still evaluates correctly. The parameters field is ignored. On the other hand, on the malicious side, we just copied a signature from some random unrelated certificate. I mean, it's not random, but it doesn't have the same TBS. So this is not going to be correctly signed. This is going to be an absolutely untrusted certificate. It's not signed correctly by the CA. However, remember that we're doing a cache poisoning trick here, and the signature is going to be ignored because this certificate is not going to be validated if we do our attack correctly. So instead of showing like a Google Slides diagram on the screen, let's show a Windows screenshot instead of certificates. So we have on the left here the original certificate of Microsoft.com. And on the right, we have a certificate where we changed the subject and the public key. So you can see here that the subject says, instead of Microsoft Corporation, it says evil and certificate. And we also added, you can't see it in the screenshot, but we added a parameters block on both sides with MD5 collisions. So this took us a few hours of computation on a GPU instance. And then we got two certificates where the left one is still trusted, and they both have the same MD5 value, as you can see at the output on the bottom. Okay, Tomer.
Thank you, Yoni. So now that it's no longer an hypothesis, let's try and actually find the target. We did it by using two methods. One was doing this locally by using some YARA rules, some scripts on our endpoints, and we came up with around 200 or so targets. We also did a cert on GitHub for the flag, the correct flag that enables the caching mechanism, and we came up with around 50 with 50 pages of code snippets that had this flag in it. So there were definitely many targets, but not a lot of them were exploitable. But we did actually manage to find one that was exploitable, which was Chrome version 48 from 2016. It was the caching mechanism was enabled, and also it did a certificate validation while going online with surfing the web, which will allow us to do some man-in-the-middle action and spoof our identity doing that way. So, Yoni.
Yeah. Okay, great. So now that we have a target, which is a browser, it's clear that we're going to attack TLS, because we have to now apply this theoretical attack to become a practical attack on TLS. Of course, TLS, where the client has this vulnerability, uses CryptoAPI with the end certificate cache enabled and without a patch on Windows. So as I said earlier, the attack has 3 phases. The first phase is going to be cache poisoning, and the second phase is going to be cache lookup, where we force the victim to look up a malicious certificate. So let's illustrate the first phase first. The first phase is a cache poisoning phase, where we take our vulnerable. Let's first assume that we have some kind of network attack going on, like a man in the middle, or we took over a router or something like that, where we can convince, or we did like DNS poisoning or whatever. We can convince the victim to connect to our server instead of the official website server. So now, of course, if we just assume this, it does not mean that we can attack TLS, because TLS is like and there's integrity checks and everything. So this is our attack is going to be to attack the TLS part. So the vulnerable Chrome is now talking to the attack server, thinking it's the official website. It's going to start out by saying a TLS client hello. And then the attack server is going to respond as part of the TLS handshake by sending the valid certificate, but modified with the MD5 collision blocks. So this is still like the valid certificate from the website, which we don't have the private key of, but we added MD5 collision blocks to it so that it would later collide with the malicious certificate. At this point, the client is going to have to take this certificate and put it in the cache. And it's going to put it in the cache with a successful validation status. So because this is still, as I said before, still trusted. Now, at some point in the TLS handshake, if you're a TLS aficionado, you might know that in some point of the TLS handshake, you might need to use this certificate's private key for some things. For example, you might have a Diffie-Hellman key exchange. In the Diffie-Hellman key exchange, the server has to sign its public part. That's not really an issue, because there is someone who does know the private key of this certificate, and that's the real server. So if we have like a Diffie-Hellman key exchange, for example, we can just go to the real server and say, hey, this is the Diffie-Hellman key exchange, sign it. And then they would say, or we can talk to them and they would give us their public part signed, and that's what we would feed to the client, like some kind of man-in-the-middle attack. So this is not a problem. The real problem comes later when the handshake continues and starts to reach its conclusion. At the end of the TLS handshake, we have something very scary to someone who doesn't have the private key, and that's the integrity checks. We have to compute some kind of HMAC with some like master secret, all the TLS things, and we cannot pass this phase without knowing the private key. So at this point, instead of finishing the handshake, we do the rudest possible thing that we can do to the client, which is to just terminate the connection. So we just like give up on this connection. Now, the client is not too worried about such a thing. Connections can drop, it happens. You might have bad Wi-Fi. Of course, it might be the case that you're at DEF CON and somebody's attacking your machine, but this is not usually the case. So usually, Chrome would see this as not something malicious, but just like some random problem. It would just try to reconnect even silently, because instead of showing a network error and forcing the user to refresh, it would just refresh for the user and just continue normally. That means that Chrome, without any warning, without any notification to the user, would try to reconnect to the server. But at this point, the attack server is going to go into the second phase. Remember, the valid certificate is already in the cache. So the second phase is the lookup phase, and for this, the attack server is now going to serve the malicious certificate instead of the valid modified certificate. And for the malicious certificate, we do have the private key, so we can use it to complete the TLS handshake. It is incorrectly signed, so it's not supposed to be trusted, but the trust status is not going to be checked from the certificate, it's going to be checked from the cache. And since this has the same MD5 value as something valid that is already in the cache, it's just going to be trusted regardless of whether the signature is correct or not. So then we have a malicious certificate that is trusted, and the continuation is just to complete the TLS handshake and serve our website. So then we can serve a malicious website and we win as attackers.
Sure, so thank you. So this is the demo part. As you can see on the left, we have the victim's machine, which is going to be with, it's going to run with Chrome version 48, and is going to try to connect to the Linux machine on the right, which is going to have two Python scripts. One is going to be the man in the middle, which Yoni just outlined how we implemented that, and another just a default HTTP server that's going to serve a malicious website to the user. Okay, so now the user is trying to go to Microsoft.com. It will reach the Firefox. It will reach the Linux on the other end. The Linux will do its man in the middle and serve a malicious website to the victim. Now we're going to check what certificate it has, it's gotten. And when we view the certificate, it's going to be the malicious certificate. And we spoofed our identity successfully. That's it.
So, to conclude the talk, some takeaways. First of all, look at the bugs reported by the NSA and GCHQ. They make for very interesting end days. This started as a bug that was there was no information on, and we got something very interesting out of it. Second thing, MD5 is still used after 2008. It's even used near the crime scene. It's used near certificates. So that's kind of something interesting to note. Third thing is there is an interesting bug class to consider here, which is you have a hash table and you assume that the hash doesn't have collision, so maybe you just forgo the comparison of the key. This is possibly not a good idea if the hash does turn out to have collisions. And last but not least, don't forget, from time to time it turns out to help to know that MD5 collisions are super easy to compute. So that's it. We'll take any questions if you have any. What?
You focus on the browser, but have you checked on other tools like software system if they are all built this way?
Yeah, there are some other paths that we considered, and we did some early checkups, and we had to stop at some point. But yes, there are some other applications that use it and are might be vulnerable to it.
Also might be something that used to be vulnerable. We don't know.
Yeah.
There's a microphone in the middle of the room.
Yeah. Okay.
So there's a microphone over there if anybody wants to ask a question. That's okay.
Great. So catch us around here if you want.
Woo.